So last time, we wanted to solve overdetermined systems. That is systems of this type, where this is A is m by n, and m is bigger than n. So we know that in general, these systems will not have a solution. So why? In general, no solution exists. Just a reminder that why is that? Because the column space of A, which is a subspace of Rm, the columns in A are m component columns, and there are only n of them. And since n is less than m, so they cannot form a basis. So the space which is generated by a span of these columns is only a subspace of Rm. And so what is possible? B may not be in this subspace. It's a possibility, and a rather large possibility. So suppose even if I consider 3 R3, so what could happen? So if I'm considering, for example, 3 by 2 kind of system. So I have 3 component vectors, but only 2 of them in A. So they generate some subspace. So I'm just denoting it by this kind of a 2-dimensional plane. They denote 2-dimensional subspace. While the whole space is R3, it has a lot more going on. And this B, in general, would be pointing in some direction. And you have no reason to expect that it will lie in this one plane. Out of all the infinite plane, it will lie in this plane. In the special case, when the B is in this plane, then you will have a solution, but not otherwise. Because if you look over here, what's happening here? You are making linear combinations of column vectors of A through the numbers in X. So the left-hand side lives in R of A, but the right-hand side may not be in this column space of A. So that's the issue. So instead, and why do we want to solve this problem? We want to get an approximate. We know that the exact solution will not exist. And in those cases where exact solution does not exist, we will try to get some kind of a best solution, which is very near to being the best, being to be a solution of this. And why we need it? Because we can use it to model data, make models of some data we have, as we discussed last time, and we will see some examples of this in action, in practice today. So the solution does not exist. So instead, look for the closest solution. What do I mean by look for an X such that it's not a solution, but when I act with this matrix on this X minus B. If it were a solution, this would be 0, but this is not 0. This is some vector you get depending on what X you put in over here. That's why I have put in an X in this argument. You just get some vector R is smallest in the sense that its length is a very small vector. It's the smallest possible, not a very small, but it's the smallest possible you can do. Its length is small. If it were a solution, the length would be 0, but it's non-zero. So, but you are looking for something which gives you the smallest, the something which is nearest possible to 0, given that you are living in this space, that X is, AX is living in this subspace, column space of Ra. So this subspace is R of A. And when you act with A of X, you get some vector here. This is A of X. And since B is not lying in this space, you cannot cancel A of X against B. That's the issue. Instead, you are looking for this vector. This is B. And this one is R of X. Is the difference of AX and B. Because from this equation, I have, this is not R of X, this is minus R of X. So let's call it Z. This is minus R of X. Let's call this vector Z. Because AX minus R of X is equal to B. So AX plus this vector Z is equal to B. And that's what you see in this diagram. You go in the direction of AX, and then you go above in the direction of Z, you get the B. Now, the thing about this Z is that you want this Z to be, we want Z to be in orthogonal to the space R of A. Then it would be the smallest one. So you can see from the context over here, I want to go to the B from this space R of A, because whatever X I choose, when I act with A on this X, I land in this subspace R of A. Now, if I get this vector, then it's not the, if I get this vector, then a Z which I add to it to go back and construct B will be longer than the one which I have constructed in the actual diagram. Why? Because it will not be perpendicular to this space R of A. Anything which you do which is not perpendicular will have more length to it. So you want to choose this particular X, which gives you this particular A of X, so that when you go back up to B, this Z is perpendicular to R of A. So this is what you want. This thing will have the minimum length. So if I call this vector as P, then this belongs to R of A. And the total space, the full space, is just R of A and plus a direct sum with the orthogonal component. What does this mean? That means any vector in over here I can write as a sum, a unique sum of these orthogonal vectors. I'll talk about this more in a bit. This is called the direct sum of two subspaces. But what really we are doing, which is clear from this diagram, is that if I take any vector, any b, I'm given any b, I can resolve it into a component in this R of A, and then I will have to add to it another component which is perpendicular to this column space. So I can resolve any vector into a subspace plus something which is coming from the orthogonal complement of that subspace. It's nothing special about the column space of A. You can do it for any space. You're given, if you are in a space R of M, you choose an S, which is a subspace of R of M, then any vector in R of M can be written as U plus, let's say, T, where U is in this subspace S and T is in subspace which is orthogonal to S. And this decomposition is unique. So we are making use of this decomposition. We have a B, we are resolving it into a, component in R of A and adding to it something which is perpendicular to this component. And this will be unique. Any other vector I choose in R of A by choosing a different A. So remember, when I choose a different X, X is my solution, I generate different vectors in R of A. But I'm going to pick that vector, that unique vector, which gives me B as a sum of something here and something perpendicular to vectors in R of A. This thing. And this will be a unique decomposition. So from here, this is P. So I'm saying P plus Z is equal to B. That's it. Over here. Then you can write B minus P is equal to Z, and Z belongs to the orthogonal complement, the perpendicular space, and which is also equal to minus R of X So this implies that R of X, the difference, belongs to this orthogonal complement. If minus R of X lives there, R of X also lives there. It's just pointing in the other direction. So this was B. This is R of X. And they live in the same space, same subspace. Now I use my theorem. I know that this space is same as the null space of the transpose of A. So that means this R of X will belong to the null space of A transpose. And it's not just any R of X, it's the R of X which is minimal. Because I will get the minimal R of X if I write it as a difference of this B and P. Now this means, this is just a statement that this is just the statement that A transpose R of X is, which is A transpose because R of X is B minus A of X is 0. Or A transpose of B is equal to A transpose A of X. So this is the condition which we have to solve for. We have changed our problem to this problem where now A transpose A is because A transpose is n by m and A is m by n. So A transpose A is a n by n matrix. And it's acting on an X, which is a n column. And this guy is also, when you act on B with the A transpose, you have n by m acting on m by 1, so you get a n column. So now you're solving an n by n system, and a unique solution will exist if this n by n system, all the n column vectors are linearly independent, or in other words, if rank of A is n, this was m by n, then a unique solution will exist. In any case, we can do this, and this will give us a solution to our equation, the best solution we have. So geometrically, again, this is very important. You have this B, you want to construct something, you know that when you will act on by A on any X, then you will get something in this subspace. Out of all these things you can make by choosing different X, you want to pick this particular one from which you go to the B by a 90 angle. Others will have a different angle when you go towards B. So pick that one which goes towards B by a 90 angle. And this is always possible because you can decompose any B into some vector in any subspace, like this is a subspace, plus some vector from the orthogonal complement. And that's exactly what we have done. So, and this decomposition is unique. Now, let's me tell you, maybe I should talk about it a little bit. Then what is this unique decomposition? This is called the direct sum. So if you have, if U and V are subspaces of a vector space W, like in this case, W is Rm, and in this case, so a vector space, a subspace of vector space W, then, and each, if this holds, each W belonging to each vector in W can be written as U plus V, where U belongs to U this subspace U and V belongs to the subspace V in a unique way. This is important. Then we say that this full space U, it splits up, it kinds of split, full space W splits up this in this kind of fashion. That's exactly just this statement, that this any vector in this W can be written as a sum of U plus V in a unique way. So it's kind of a splitting of your vector space. So this is called the direct sum. So for example, in R3, I can give you this splitting. Choose this plane, and this is one subspace, and this is the other subspace, R2 plus R1. So R3 is like this, because any vector here I can write as a vector in R2, which is x, y, 0, plus a vector in the other space, which is 0, 0, which takes this form 0, 0, z. And this decomposition is unique. If I have x, y, and z fixed, this is the only way I can write them. This belongs to R2, this particular R2, and this belongs to R1. So R3 is a direct sum of R2 plus R1, and you can choose different R2 depending on what plane you choose over here. So if you have orthogonal spaces, if S is a subspace, then if you consider the orthogonal complement, then your vector space of which S is a subspace you are guaranteed that it will split as a direct sum of S and its orthogonal complement. Essentially what I have done over here. Why is that the case? Because we already know that if you have S has dimension, it's a subspace, it has some dimension, let's say P, and then S perpendicular is also a subspace and it has dimension Q, then P plus Q is equal to N, which is the dimension of the full space. So I can pick a basis for S. This is a basis for S, and add to it the basis for S perpendicular. Let's number them. Like this. And we know because these guys are orthogonal, everyone in over here is orthogonal to vectors over here. So they are linearly independent. We already know that. So this whole thing, now I have n linearly independent vectors. So I have a basis for the full space Rn or V for the full space, which is n dimensional. So any vector in V will then be able to, I will be able to write like this, because it's a basis. I can expand any vector in this basis. But this part lives in S, and this part lives in S perpendicular. So I've written this vector as a sum of, let's call it Vs plus Vs perpendicular, where this belongs here and this belongs here. All I have to do is show that this decomposition is unique. which it is, because suppose if this V, I have written it as V plus, let's say it's uh, this space, let's call this vector as V1. V1 I have used over here. Let's call it, so let me just use these symbols which I have used. So, but suppose I can also write it as some other splitting where you still have this y and z living in the corresponding subspace and its orthogonal complement. Then since these two vectors are equal, so I can write and this gives me this difference is equal to this difference. But since y lives in S and Vs lives in S, so this right left hand side lives in S. But since Z lives in S perpendicular and V S perpendicular also lives in S perpendicular, so this difference lives in S perpendicular. So I have a vector, this vector which is equal to this vector. This vector lives in S, but this vector also lives in S perpendicular. And we know that the only thing common between two orthogonal subspaces is 0. So that means this vector is the 0 vector, which gives me immediately this result that this y is actually equal to ys and z is equal to vs perpendicular, the original vectors. So that's the only decomposition you have, nothing else. Geometrically, it's very clear. You have an arbitrary vector. You are putting a projection onto your desired subspace. Orthogonal projection. When you do the orthogonal projection, you get a particular unique vector. And that's the only way you can split them. Now let's consider an example. So suppose you have this system. It's an overdetermined system. So the system is 1 minus 2, 2, 1, 3 minus 1. That's the system which we are trying to solve. So just by using our methods, this is the augmented matrix which we are dealing with. And I try to bring it to the echelon form. So 2 times the first row added to the second. And minus 2 times the first row added to the last. Minus 6 plus 2 minus 4. From here, I can bring the ones by dividing by 5 here and dividing by minus 3 here. Now from here, when I make it the echelon, so minus 1 times the second row added below, I get something non-zero, some number here and a 0 row here. And we know that this means A zero row equal to some non-zero number means inconsistent system. No solution exists. And this essentially means that this vector cannot be written as a linear combination of these two column vectors. There's just no way you can do it. You can try guessing it right here. For example, choosing a equals to 2, b is equal to 1 to make a 2 plus 1 over here at 3, but this will mess up the others. If you try some other components, it will just keep messing up. And the proof is that using this row echelon form. So instead, let us set the least square problem. Solve for the least square solution. You call it square because you are constructing A transpose A. So it's kind of a you're squaring the problem. So I have to construct this A transpose A. I have 1 minus 2 is the transpose of my original matrix. And multiplying it with the matrix. And this guy, because now it's going to become a 2 by 2, it has to act on this column. And on the right hand side, I have this matrix transpose acting on B, which was 3, 1, 2. So when I do this, I get 1 plus 4 plus 4 are 9, and 2 minus 6 minus 2 2 minus 6 minus 2, so it should be a minus 6. Just 1 second, let me look at my notes. Sorry, this was, let me look at the matrix. It's 2 minus 2, 1, 3 minus 1. So this is a 1. 1, 3 minus 1. So this gives me 1 minus 6 minus 2. So this gives me minus 7. And similarly here, I have a 1 minus 6 minus 2. So again, minus 7. And the last one gives me 1 plus 9 plus 1, 11. And the right hand side gives me 3 minus 2 plus 2, 3 minus 2 plus 4, so it gives me a 5, and 3 plus 3, 6 minus 2, or 4. So that is just a 2 by 2 system that needs to be solved. And you can easily do it using your usual methods. And we know that it's a square system, and this is not a this matrix is not singular, so it's going to have a unique solution. The solution is going to exist, and it's going to be a unique solution. So if you do it, let me not, since it's a, we have done these things many times, so let's just not, let me just not complete it, just find the solution. And it turns out to be 83 over 50, 71 over 50. I'm just looking at my notes, don't want to write the whole thing. Now let's see how it's used in fitting the data, because that's the main application which we are looking at. So suppose you are given these three data points. That for x is equal to 0, y is 1. For x is equal to 3, y is 4. For x is equal to 6, y is 5. So you have a point here. Then you move x to 3, you get a 2, 3, a point here. Then a point here. So you're trying to kind of draw, and this is your data, and your model is a line. So in other words, you want to fit this data to a line or linear relation between x and y. That is, you write something like this, and you want to find out, let's write it this way. Well, it's okay. You want to find out A and B, because that will define your line. So there's some line which is closest to all of them, and that's the one which you want to find. None of them lies on it, because if they lied on it, then it will be an exact solution. But they're not coming from an exact solution. They're not following this line, but you just want to find a line which is closest to them. So what you have, you just plot these points and fit them in this line. So you have y is equal to 1 is equal to 0. A plus b. Then you have y is equal to 3 is equal to a times 4 plus b. You don't know what is a and b. You're trying to find them. Then y is equal to 5 and y is equal to 5 and a is equal to 6 plus b. So these are the equations you have at your hand. So you can write it as a matrix equation, but it turns out to be an overdetermined system. So if you had only 2 points, you can see that it will not be an overdetermined system, and a solution will be guaranteed. Because geometrically also, if you have just 2 points, I can always draw a line through them. But if I have 3, there's no single line which passes through 3 unless they are very special and lie on that line. So this thing I can write as a matrix because I have this B and A. I could have written the other way. And this gives me this result. 1, well, y was 4, sorry. Looking at this data, y was 4 here, and x was 3. So these equations, which are just data fitting into putting into your model over here, gives you this matrix equation. And it's an overdetermined system. So we look for least square solution. This is your A, this is your B, and this is the X you are trying to find. So you compute AT times A, it gives you 1, 1, 1, 0, 3, 6. 1 plus 1 plus 1 gives you a 3 here. 0 plus 3 plus 6 gives you a 9 here. 0 plus 3 plus 6 gives you a 9 here. And because when you go 8t times a, and then you have 3 times 3, 9, and 36, 45. And you're trying to solve at times ax is equal to a times at times b. So when you do AT, which is 1, 1, 1, 0, 3, 6, you act on 1, 4, 5, you get 1 plus 4 plus 5, which is a 10, then you get 0 plus 12 plus 30, 42. That means you have to solve this system. X1, actually X is now, I shouldn't call it X1, X2, because I have written this vector as B and A. So this is B, A. The first variable is B, the second is A. So it's this thing. Let me see if we can solve it quickly. So I can multiply by -3 the first row and add 2 the last one. I get 0 and minus 27 plus 45, that's 18, and then minus 30 plus 42, that's a 12, and now I can divide by 18 on the last line. I get 12 over 18 is a 2 by 3. Now I can bring it to the reduced form by multiplying the last line by -9 and adding above. Three, 0, and 10 minus 9 into 2 by 3. So that's a 4. And then the first row I can divide by 1. So here is my solution because it's now the reduced echelon form. It says B is 4 by 3 and A is 2 by 3. So my model, the best fit for that data would be 4 by 3. Similarly, I can take an example that you're trying to fit a quadratic formula, a quadratic model, that you know that for example, the data is way too scattered like this, and for some reason, or looking at data, or someone has told you that you want to fit it to a quadratic model. So suppose this is the data you are given. I did an example of 3 data points, but in general, you will have more. I just don't want to deal with big matrices because in practice, you deal with these matrices using some computer program. When we are doing it with hands, so we are just limited to do those examples which are small enough so that we can deal with these matrices by hand. But otherwise, these methods are usually employed for large matrices, large data points, but your computer can easily handle. You still have to understand that what's going on. So that's the whole point. So suppose this is the data. It's not lying on a quadratic function like this point. If I say that 4 is the square root of 2, but 4 is not the square root of 3. So, but I want to find what kind of a quadratic function can best describe it. So that's my general quadratic function. And I want to find A, B, and C. So I can just start putting these data points over here. I just have to do is make a column for x square. Zero, 1, 2, 3, and 9. So what you have to put it over here. You have 3 is equal to A times 0 plus B times 0, that's the first data point, plus C. Then you have 2 is equal to 1 times A times 1 plus B times 1 plus C. Then the third data point is Y is equal to 4, and A is being multiplied by 2 square, which is 4, and B is multiplying with X, which is 2. Then you have the last data point where Y is again 4, and it's being multiplied with X square, which is 9 times A plus 3 times B plus C. Just putting these data over here. So now you have generated this. You have 3 unknowns. A, B, let me write them as C, B, A, because I'm starting with this row. Uh, and then the second row is of these corresponding to B. So now if I do the matrix multiplication, on the right hand side I have 3, 2, 4, 4. Now you can see if I do the matrix multiplication, so like for example, if I look at this row, I have C plus B plus A, this line equal to 2. This gives me the third equation, C plus 2B plus 4A is equal to 4. So again, it's an overdetermined system, and I don't know if I can create uh, so so a solution, exact solution does not exist. I can just look at it to get 3 over here. If I try to solve it, to get a 3 over here, making a 3 by a linear combination of these columns, I know that the first column has to be multiplied by 3. But it's too restrictive. I won't be able to cancel the other things to get the other satisfied. So an exact solution will not exist. Instead, this would be my A, this would be my B, and I will create A transpose A, which is 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9. So when I multiply this, then I get because I have uh, sorry, I have 1 plus 1 plus 1, 4. The next line gives me 1 plus 2 plus 3, a 6. The next line gives me 1 plus 4 plus 9. So that's just a 14. This gives me 1 plus 2 plus 3, a 6. And then 14. Then 0 plus 1 plus 8. 9 into 3, 27, 36. So this acts on your CBA, and you have to then multiply this matrix on, so right hand side becomes 13, 22, and 54. So it's a little bit complicated 3 by 3 system, and all you are doing is solving these. So you can solve it and find the values of C, B, and A. So suppose I get some value C dash, B dash, A dash, which is guaranteed to come out of it. and then you will have your model. And whatever these numbers come out to be, those numbers are the ones which are a closest uh, quadratic model to your data. So I think I'm done for today, and I'm gonna stop it here.